Here I am again, class, Professor Kleinian. This is chapter 20 in the book, homework packet. This is just the multiple choice part of it, dealing with electrochemistry. Let's get started. So the number one question here is to list in order of increasing oxidation number the sulfur atoms from most negative to most positive. Okay, so it turns out the answer is this first one here, A. And the reason I know that is because sulfur gets progressively more positive as you go across here. Now that's not true of the other answers. For example, let me show you that in the first case it's called copper sulfide, it's -2. In the case of this one, if you break it down, K2S2O3, so what that means is that, so this is a +2, this is a -6, meaning that this must be a +4 here, but divided by 2 must mean each of these is +2. And the next one here, SO2, well that's when it's +4. And then over here, the sulfate, SO4, 2 minus means the sulfur here, that's -8. So if you look at it this way, this is -8. The whole thing here has to net out to 2 minus. So then that means the sulfur X here is going to be, so -8 has to net out. See, this has to be +6. So the progression is -2, +2, +4, and +6. So that's why A here is the correct answer. Okay, next question. Use the reduction potentials to determine which of them is the reactions thermodynamically favored. Okay, so what that means is that the E potential here must be positive. If you have any negative ones generated here, well, that would mean it's unfavored. Okay, so then I went through and worked this out. All of these are negative except for C. So let me show you how that works. If you look, first of all, figure out what is oxidized and what is reduced. CD goes from 2+ to 0, so notice that number went down. It's the reduced one. Put an R there. This is the one that's oxidized, so it has to go last in the equation. So first of all, the reduced one, the cadmium here, is going to be a -0.403. Okay, so far that doesn't look very promising, a negative number there for the reduced one. However, the manganese, you have to subtract these off, remember. The manganese is -1.18. So that's when you go ahead and change these to the positive numbers. This is quite a bit bigger than this, so the entire cell now has a positive. When you add these together, it's a positive number, so that's why it's C. Okay, so what's the coefficient for this following the redox using the smallest whole number coefficients? Now you need to know how to balance these redox reactions in acidic and basic environments. Now they're telling us this is acidic. I'm going to ignore for the moment everything that is not directly a part of the redox here, because you see those are going to come in later anyway. And just focus in on, first of all, writing down the 2 half reactions. Okay, so I do notice that the chromium here is going to be either the oxidized or the reduced one. So I'm going to just write that in here. Now what is it? Well, this one is -14. So it has to net out -2. That means this is going to be +6. Here, hang on a second, let me show you. So this is -14 because of 7 oxygens. This whole thing here nets out at -2. And then over here you've got, this is going to be -12. So this is really going to be +6 plus a +6. Because see, you have 2 of them. So the chromium went from +6 to +3, so that was reduced. This is going to be the one reduced here in the end. Okay, the other half reaction is going to involve the manganese, so let me give myself some room here. Manganese 2 plus, let's see, it's going to become this manganese with 4 oxygens and 1 minus. Okay, so make sure we got it all right. Alright, very good. Let's see if I can get my eraser working here once in a while. I guess I'm not sure it's going to work here. That probably, oh, I did erase it. Excellent. I got my eraser working. Okay, so now going back to this, we need to do some work on this side, then some work on this side, then recombine them. So the first thing to do is balance all the atoms here that are not oxygen or hydrogen. And so see, first step is to put a 2 here to balance the chromiums. Next step is to balance the oxygens, and since I have 7, I need to add 7 waters over here. See, just, I know it looks strange, but water is a part of the reaction, and so this gives me 7 oxygens on both sides. Now, because I added hydrogens over here, to balance that out, I'm going to need to put the hydrogens on the other side. So to do that, notice it's going to be 14 H pluses, because I have 14 hydrogens and they all come in as H plus. So this is good. The next thing to worry about is how many electrons get moved from one side to the other. You do that by balancing the charges. So over here I have 14 plus. See, this is 2 minus. Over here I have 6 plus, 3 plus times 2, and nothing. So over here the entire plus is 6 plus. When you subtract these, you get 12 plus on this side. So 12 plus on this side, 6 plus on this side. These need to equal, and the only way you can do that is to bring this down to this level by adding 6 electrons to this side. So now you see adding 6 electrons to the plus 12 brings this down to plus 6. So now these are both equal. So notice on this side I have to add 6 electrons. Just notice that. Over here, let's do some more work now. Alright, so the manganeses are already balanced. I need to add 4 waters to this side to give me my oxygens over here, and then of course I've got 8 hydrogens, so I'm going to go ahead and put the 8 hydrogens over here. Alright, all the elements are balanced. Now I just have to worry about balancing the charges like I did over there. This whole side has 2 plus. This whole side has 8 plus minus 1, or 7 plus. So let me write that down. This side has 7 plus, and this side only has 2 plus. So I have to make these equal by reducing this one down to that. So that means I'm going to have to add 5 electrons to this side, because now 7 plus plus 5 minus is equal to 2 plus. Okay, so now here we go. I had to add 6 electrons to this side and 5 electrons to this side. So that's where it gets a little tricky. In order to balance this out, I'm going to have the same numbers of electrons on both sides. So, as much as you may not like it, I have to multiply this whole side here by the number over here, which is 6. So notice I'm going to put it right here, small. Over here, I have to multiply this whole side, as much as you may not like it, by the number over here, 5. You'll see in a second why that is, because you have to have the same numbers of electrons on both sides. Okay, so now having multiplied this by 5, I'm going to do that with all of these. So, oh my gosh, how many hydrogens? 14 times 5 is, what is that, 84? I think that's 84 hydrogens. And then for chromium, I would multiply by 5, so it's going to be 5 Cr2O7s, 2 minus, okay? And then multiply this, make sure I've got everything. Oh, I've got to add my electrons too over here, so that's going to be 30 electrons. So that's the key. Then over here on this side of the arrow, I've got to multiply 2 times 5 for 10, chromiums, 3 plus. So notice that's going to be right, 5 times 2 and 10. And then I have to multiply 7 times 5 for 35 waters. Okay, so much for that side. Over here, I've got to multiply everything over here by 6. So 6 manganeses, and I had to add 4 waters. So I'm putting my 4 waters right there, and that looks like everything on this side. Over here, I've got 6 of these, and I'm going to multiply 8 times 6 for a total of 48 hydrogen ions, and last but not least, 30 electrons. Okay, I might be running off my screen there, so that's what I'm going to do. Alright, now, in fact, right now I have the answer to this problem because the coefficient for the manganese has already appeared, and notice the coefficient here is going to be 6. So I don't have to combine these and everything else, because once you get to this stage, you know the coefficient here is 5 for the chromium and 6. But just for the sake of discussion, let me go ahead and finish this to show you what the answer would be. Because you see, oh, before I cross them out, let me recombine. So forget what I just did there. Can I get rid of that? Okay, good. Let me recombine everything. So 30 electrons plus 84 hydrogen ions plus 5 of these. So that covers everything on this side. Now I got to pick up this side. So I'm bringing everything that's on the left together like this. And the 4 waters. So wait, but it's 4 waters times 6. Whew, I almost made a mistake. 4 waters times 6. 6 times 4. Okay, so in fact, I needed to have 24 waters here. So just to make sure I don't make a mistake. Alright, so then I'm going to put in the 24 waters here. So I needed to multiply that by 6. Alright, now over on this side, I'm going to regroup everything over here. So that's 10 chromiums, 3 plus, and 35 waters. This thing is getting crazy. And over here, I have to bring that down now. That's 6 of these, and 48 of these, and 30 electrons. Okay, if that doesn't look spooky. So now I'm going to start crossing out things. See, the electrons are the first thing I cross out. Then the next thing I want to work on is the waters. On this side I have 24 waters. So over here I have 35 waters. That means I'm going to have 11 more waters on this side. So I'm crossing this out and putting 11 waters here. And of course now that's going away completely. Here I have 84 hydrogens, and over here I have 48. So 84 minus 48 nets me out at 36. So I'm going to have 36 hydrogens on this side, and these are going to completely go away. Alright, so the final answer is ready to come. You're going to need 36 hydrogen ions on this side, plus 5 of these dichromate things, and 6 manganeses. And then on this side, it's going to be 10 of these chromiums, ions, and 11 waters, and 6 of these, 1 minus, and that's it. So just to double check, did I do this right? So the way you would check is, first of all, check to make sure you got the atoms balanced. So I have 10 chromiums on both sides, that's good. I have 6 manganeses on both sides. Let's see, for oxygens I have 7 times 5, or so 7 times 5, so 35 on this side. Over here I've got 11 oxygens, and over here I have 6 times 4, 24. So I've got 35 on this side too, that's oxygens. Hydrogens, I've got 11 times 2 is 22. Hydrogens on this side. And over here I've got 36 on this side. What am I missing? Did I lose something in here? 48, 64. No, maybe I made a mistake in there somewhere. But definitely the answer to the question is there should be a 6 in front of the manganese. So at least I've got that part right. Okay, so the answer again is the 6 here. Try to attempt to get it finished, but I don't want to waste time with it right now. Maybe I made some small mistake in there. Okay, which element can have the highest positive oxidation number? Well, this, I think the maximum is probably 3 plus. Carbon, I don't know, 4 plus maybe. Nitrogen, what would that be? I'm not sure, maybe 5 plus. I know chlorine can have this, Cl O4, a 1 minus. I've seen that before, perchlorate. So that's 8 minus. And that's going to make this 7 plus. So that's pretty positive. I'm going to have to say chlorine is going to have the highest possible oxidation number. Okay, so now we can move a little faster. Magnesium reacts with dilute hydrochloric acid to produce hydrogen gas. Okay, so silver does not react with dilute hydrochloric acid, so that is going to rule out that one. And first of all, notice that magnesium reacts with hydrochloric acid, so see, it's not going to react with hydrogen gas. And let's look at this one. So this has actually got it backwards. You're not going to have silver taking out magnesium, which is higher on the reduction chart. So by default, this looks to be the answer. This one should occur as written because magnesium certainly will want to be oxidized, and it will oxidize about anything. So the answer should be C. Okay, use the following information to answer questions 6 through 8. So the cell potential, which one is going to be the oxidized one, which is the reduced one? So because this is more negative, this is the one that's going to be the oxidation one. And this is more positive, it's the reduction. So it's going to be 0.80 minus a negative 2.37. So see, that's going to be a fairly high potential. That's 3.27 plus 0.8. Man, what does that have to be? 2.37 plus 0.8. Looks to me, unless I'm incorrect, it should be 3.17. Just adding up these numbers. Use the following information to answer questions 6 through 8. A cell is set up using the following half reactions as in standard conditions. Okay, so what are the products of the reaction? Alright, so in this case, the products of the reaction are going to be manganese ion and solid silver. Now what if you reduce this to 0.5 molar? So notice what's going on in the reaction. We start out with manganese metal and 2 silver ions. This is the way it's going to run. These are +1, and it's going to become 2 silver metals and magnesium 2+. So if you take out some of the standard concentration, don't forget it's 1.0 molar standard, so this is actually lower than standard. Taking that out means it's going to drive the reaction to the right to try to replace some of that, according to Le Chatelier. You would think that would increase the potential then, because it's driving it in a favorable direction. The following reaction is in aqueous solutions balanced using the whole numbers of coefficients. What is the coefficient for H? Okay, here's another one of those balancing chemical reactions, redox reactions. So, well, let's just get right into it. Alright, so this is good, should be good practice for you to know how to assign oxidation numbers, and this thing has just got all kinds of stuff to worry about. Okay, then the other half reaction is going to be the NO2 becoming nitrate. Alright, let's do some work on this. So I need to get some oxygens over here. I'm going to add 2 waters to this side, and therefore I have to add 4 hydrogen pluses to this side to balance out those hydrogens. And then before I leave it, let's balance out the charges here. So +4 plus -1 is +3 on this side. And this whole thing is 0, so it means I'm going to have to add 3 electrons to this side. That should be what I need to do, so keep that in mind. Just get rid of that so it doesn't confuse me later. Alright, well that's good enough for this side. Let's take a look at this. So here I need to add 1 water to this side to give me an extra oxygen, and I'm going to have to add 2 hydrogen ions to this side. Okay, so now let's do the little balancing of charges thing. 0 charges, over here I've got -1 plus 2 plus, so that's 1 plus total. When you subtract those, 0. So I'm going to have to add 1 electron to this side because I want to bring this down to 0. So that's where I add my 1 electron. Okay, so now we're at the point where we could recombine both of these, but before we do that, we need to make sure we have the same numbers of electrons on both sides. So it's 3 and 1 means all I need to do is just multiply this one by 3. Then I'll have 3 electrons on both sides. They're making it easy on us here. Okay, so 3 NO2s plus 1 water. I'm not going to lose anything here. I'm not going to make a mistake. 3 NO3, 1 minus. And 3 times 2 is actually 6 hydrogen ions and 3 electrons. So 3, 3, 3, and I have to multiply the water by 3 too. So now I'll make a mistake here. 3 and 3 and 3 and 6 and 3. Okay, so now I could actually combine all these together because you see over here I didn't have to multiply this at all. So, but let me just rewrite it again so I don't make a dumb mistake like I always seem to be doing. And MnO4, 1 minus, and here is MnO2 plus 2 waters. Okay, so now I'm going to go ahead and recombine everything. 4H plus 3 electrons plus MnO4, 1 minus. On this side, I have to pull in all the stuff from over here. 3 NO2s and 3 waters on this side. Alright, that's on the 1 arrow side. Now over here, here is MnO2 and 2 waters. And over here we have 3 nitrates and 6 hydrogens and 3 electrons. So crossing out my electrons, hydrogens I have 4, where I have 6, so I'm going to leave myself with 2 hydrogens here. Got 3 waters on this side and 2 here, so that's going to leave me with 1 water here. This is a relatively easier one than the other one, so it's going to be manganese 1 minus plus 3 NO2s. Everything else went away except for 1 water, and over here it's going to be MnO2 and 3 NO3s, 1 minus, and 2 hydrogen ions. Okay, to check to see if I got this completely right, 1 manganese, 3 nitrogens, 6 oxygens, plus 1 is 7, 8, 9, 10, 11 oxygens. Over here I've got 9 oxygens, 10, 11, very good. Hydrogens over here I've got 2, and over here I've got 2. Charges on this side I've got 1 minus total. Over here I have 3 minus plus 2 minus 1 minus, so that is the correct answer. And so the original question, what's the coefficient in front of H plus? So we really did have to finish this to get to that point. The coefficient was 2. So good luck on these, guys. There's a lot to do, and it's easy to get lost. Well, maybe this is an easier one. Which is most easily oxidized? That's the one that has the most negative potential, and it's going to be in this form. So the thing that's most easily oxidized is the aluminum atom, not the ion. Okay, that's the already oxidized part. Calculate the cell potential for this, suitably connected. So the more negative one is this, that's going to be the one oxidized. This is the one reduced. So therefore the math is going to turn out to be like this, minus negative 1.66, okay, plus, so 1.66 plus 0.337. Okay, so that's going to come out to very close to 2, isn't it? Like 1.99. This looks to me like our answer is going to be 2 volts positive. Okay, use the following equation to answer these questions. Okay, so what is the oxidized and reduced substances? This is usually pretty easy. So the chlorine here is minus 6. That must mean that it's a plus 5 on this side. The only chlorine on this side is this, which is 0. So it went from plus 5 to 0. That means it was reduced. So this is the reduced one here. Here it went from minus 1 to 0. That means it was oxidized. So this is the oxidized one. Alright, so the oxidized, which is the Cl, and the reduced is this, so that means this has to be the answer. And how many electrons are transferred in the balanced equation? So to get that, we're going to have to do a little calculating. I'm not sure if I have the very easiest way to do that, but I guess what I would do would be just to start up here and balance away on it and see what I get. So I'm going to give myself some space. I'll start up here and just work down. Alright, well this is another example of balancing the redox reaction. Well, let's just take the essentials here, and everything hopefully will take care of itself. So I'm not going to worry about the hydrogen and the water. I just want to see that the half fraction here is going into chlorine. And the strange thing about this one is this half reaction is also going to chlorine. So I'm going to take away the 5 there because I'm bringing this down to bare bones. Maybe that's true, but we'll wait till later to figure that out. That should come out later in the wash. So here we're going to go to chlorine. Okay, so I took away these coefficients just to start from scratch here. Alright, and I'm going to put a 2 in front of that, and basically that's fine. -2, 0. So I need to add 2 electrons to this side. So that's now balanced, and the charges are balanced. On this side, let's see, Cl2. So I need to make 2 of these, which means I need to add 6 waters to this side, which means I need to add 12 hydrogen pluses to this side. And just putting in the electron transfer, 0 over here, plus 12, minus 2. So this is going to be plus 10 over here. Okay, so that means I need to add 10 electrons to this side. Yeah, 10 electrons. That could very well be the answer right there. So just to confirm that, notice if I have 10 electrons and then here 2 electrons, well, in the end I will have to multiply this whole thing by 5, but this is really the answer coming out right there. We're going to need to have 10 electrons, see, because this is going to be 10 and 10, so it appears like the answer is going to be 10 electrons transferred. So what a product is formed at the anode of electrolysis of sodium sulfate solution? Okay, so now the confusing thing here is the terminology. And the sodium sulfate solution, this is the famous reaction where you've got some electrodes in water actually, and the sodium sulfate is an inert compound that's not going to react. So these are just inert electrodes here. Let's say, I don't know, platinum or carbon or something. And of course in the solution you've got the sodium ions and you've got the sulfate ions. But I'm going to claim that these are just spectator ions that won't be part of the reaction. Too difficult to reduce or oxidize these. So what's really going to be changed is the water here. This is where the water is going to get split apart, and the overall reaction is going to be water splits apart into 2 hydrogens and 1 oxygen. Now if you notice, the hydrogen is 1 plus on this side and 0 here, so the hydrogen is actually reduced. The oxygen here is -2 going to 0, so it has gained electrons. No, it's lost electrons, so this is the side right here that's oxidized. That's kind of important to notice. So let's say if the electrons are leaving and going this direction, and of course don't forget, this has got to be assisted by adding a battery. That's a symbol for a battery. You have to put energy into this or you're never going to split water. The side that's being oxidized over here is releasing oxygen gas. Over here, the side that's reduced is releasing hydrogen gas. So here's the reduction side, and here's the oxidation side. So now the tricky thing is, which one is at the cathode, or the anode here, the anode? Well, according to the book, the side that's being oxidized is the anode. I guess that's the same as we had before when we were using the electrolytic cells, which means that the anode would be the oxygen, and that would be our answer. They're implying that the reduction over here would be at the cathode. So there we go. And now what about this one? Electrolysis of aqueous copper nitrate. This is a really tricky one here because the copper, if it's electrolysis, that means we're splitting the copper and the nitrate out. So copper is going to be existing here in the ion form, and nitrate also in the ion form. This is a spectator ion for sure, so something else is going to be the one that is oxidized here. In fact, don't forget that it's in an aqueous solution, so we're going to see that at this electrode, oxygen is going to be more easily oxidized than this one. So oxygen is going to be released over here, and then this is where copper is going to be plated out on this electrode. So the copper here is being reduced, and the oxygen here is being oxidized. Okay, so if the terminology is true from the last problem, the anode is where oxidation is taking place, and the cathode is where reduction is taking place. So the cathode, what's happening at the cathode would in this case would indicate that copper is coming out of the cathode. I'm a little bit confused though by the terminology here, whether that's what they really mean. But if it's consistent with what they just said before, if this is really the cathode, then copper would be plated out at the cathode. Again, I'm not sure that, in fact, the book gave this as the answer, so it's just a confusion as to which one is the cathode and which one is the anode in these type of cells. If you keep it like this, it's the same as the other one. You know, oxidation goes with A, those are vowels, and here's consonants. So I don't know. I'm a little confused by the terminology here, but other than that, it's all good. Okay, that's it for multiple choice.